As you clicked on this video, I guess you might have watched many other excellent YouTube videos about Schrodinger's equation, and perhaps feel that you still don't really get it. You may follow all the arguments for it and the maths leading to it and following on from it, but at the end it all feels sort of empty. In this video I will provide a much deeper understanding, why it applies and what it means. But be warned, this can only be done using a new, much richer version of quantum mechanics called real wave quantum mechanics. You won't find any of this in textbooks because it is a new theory. If you are new to the subject, those other videos will do a better job on introducing Schrodinger's equation, and then you can maybe come back. But if it is understanding you want, you are in the right place. There's a lot of material to cover, so I'm doing it in 3 parts. In this first part, I will focus on the role of the second partial derivative and its relationship to the potential. This term is responsible for the shapes that the wave function takes. In the second part, I will look at the first time derivative, which is all about energy. And finally, in part 3, I will look at the part played by de Broglie's superluminal matter waves, which cover motion. The main challenge to understanding is not particularly mathematical, but if you've studied normal quantum mechanics, it will require a big adjustment of the way you think about what is happening. I would ask you to stick with it. If you do, I think you will never view quantum mechanics in the same light again. So let's go. Very many years ago, as a young chemistry student, I sat and watched a chemistry lecturer carefully write this equation on the blackboard, and then spend 40 minutes explaining what each term meant. We were chemistry students. Almost by definition in those days, chemists were scientists who couldn't do maths. So we had never seen the Laplacian, let alone knowing what it meant. And then there was this imaginary number I. How could we be expected to make sense of something like that? And by the end of the lecture, fair enough, we did know the meanings of all the symbols. So that was that. We had done Schrodinger's equation. Box ticked, and we could thankfully move on to the pretty pictures. After the lecture, feeling deeply dissatisfied, I asked the lecturer the question that introduces this video. Yes, but do you really understand the Schrodinger's equation? I suppose I was a bit cheeky, and he stood on his dignity, and his answer was yes. But I can tell you, he really didn't understand it, and neither did I. Because writing an equation down and explaining what the terms mean goes absolutely nowhere to understanding what is actually going on. So when, in later life, I was given the opportunity, I started studying physics with the one goal of gaining a meaningful understanding. And what an amazing journey it has been. My first thought was that you could hardly expect a chemistry lecturer whose forte was fiddling with solutions in test tubes to know about this stuff. But of course the physics bunch would. But the more I studied, the more convinced I became that they didn't understand it either. What they did know was where it came from. And where it came from was essentially 2 acts of scientific imagination. The first was de Broglie's intuition about the harmony of the phases, which he brilliantly quantified through his expression P equals h bar k. I have done a complete video on this, and I'm going to go through it more deeply in the third part of this series, so I won't labour the point here, but since we are talking about equations, I had better just explain this one a bit. It says that the momentum of a particle, P, is related to the waviness in space of some wave, that is, how much it goes up and down per unit distance, which is known as k, or the wave vector. De Broglie showed that this wave, which became known as the matter wave, was moving faster than light, so it could not be a real wave, but it could nonetheless be telling us about something that is real. The second intuition was Schrodinger's. I'm going to go fast here because, as I said, this ground is covered ad nauseam elsewhere, and it is not what this video is about. He essentially made up a conservation of energy type of equation. He used de Broglie's momentum expression to calculate the kinetic energy of the particle, added in the potential energy, and said that these must be the same as some total energy. The first two terms, the sum of the kinetic and potential energies, are collectively known as the Hamiltonian. Then he recognised that the momentum and energy could be expressed as operators acting on the wave functions, which were the solutions of the equation. The momentum operator, as shown here in green, and the energy operator, as shown here in blue. Then, using p squared upon 2m as the expression of the kinetic energy, he could apply the operator term for the momentum twice to give the second spatial derivative of his equation. The presence of I, which he initially thought was a flaw, was found to be essential, and lo and behold, out popped all the beautiful shapes and wonderful features of the Schrodinger equation. So yes, the physics bunch knew how to plausibly obtain Schrodinger's equation and on what it was based, but I concluded that they didn't understand it either. And further, I concluded that they never could understand it because quantum mechanics is missing its foundations. There must be a deeper level of theory which normal quantum mechanics does not yet recognise. These levels must lead to Schrodinger's equation, or indeed Dirac's equation, but must also have features which allow the point-particle picture to seem reasonable, up to a point, if you'll excuse the pun. But because everything comes from P equals h bar k, which is describing motion of a point particle whose position is predicted probabilistically, you are stuck with trying to explain everything in those terms, even when the results seem weird. For example, to explain a stationary state of the hydrogen atom having orbital angular momentum, you will have to say that there is some point particle whizzing around at very high speed. How else can you explain angular momentum? Then you will have to live with particles in the inner orbitals of heavy elements travelling at close to the speed of light, and start to worry about relativistic effects on the electron. We really want a richer theory, which, while replicating quantum mechanics, has deeper foundations which will allow us to understand better what we are talking about. I have given an explanation of such a theory in other videos, but here I want to focus on why this theory makes Schrodinger's equation understandable. After all, many partial differential equations are understandable. We can interpret the second spatial derivatives as forces, as for example when we apply the wave equation to a guitar string. The curvature is a measure of how much potential energy is stored in the string, ready to induce an acceleration, which is what the second derivative in time is in these circumstances. It just makes sense. But what happens if we try to do this with the Schrodinger equation? Well, the immediate problem is that we don't know what we are talking about. In the normal interpretation, psi is a probability density. But why is the curvature of a probability density relevant? What is the curvature of a probability density anyway? And how is it leading to all those wonderful shapes? We need more. We have to get underneath quantum mechanics, literally to its foundations. But there aren't any. So we are obliged to look elsewhere to find them. I started developing real wave quantum mechanics from the established fact that if you cross acoustic waves and the waves have a particular relationship between the direction they come from and their phase on arrival, then you get rotating vortices, which have angular momentum. From here on, I'll call these field rotators, or in fact, just FRs. This picture shows waves coming from the 4 cardinal positions of the compass, with phase progressively differing by 90 degrees as they pass through the FR. Alter the order in which the waves arrive, and you reverse the spin. Actually, 4 waves give rise to a grid of FRs rotating alternately in opposite directions. Well, that's not quantum mechanics, but it gives us a handle on spin angular momentum and is suggestive of some form of extended structure. So we apply some what-ifs and see where we get to. I am going fast through these as they are fully discussed in these 2 videos. What if FRs interacted with each other? Say that a small fraction of the waves making them up gets absorbed and re-radiated as a spiral wave. This is not a novel assumption. Think of Huygens' principle, where each point on a wavefront generates a new wavelet and the main wave is the tangent of all these wavelets. The difference is that our wavelets are spirals rather than spherical. The ratio of re-radiated to received waves can be a dimensionless characteristic of the theory. Shall we call it alpha? But where is the energy coming from? It's a bit chicken and egg, but structures must be losing empty waves. These are real physical waves carrying momentum and energy, but they are not in phase direction correlation. So there is no angular momentum or contribution to the mass of the structure. But if structures exist, and we know there are plenty of electrons in the universe, then we are going to have a lot of empty waves buzzing around in the vacuum, which for us we could better describe in the old-fashioned way as an ether. So our second postulate, we are just asking that the FRs act like aerials and pick up some amplitude, a gain if you will, from this stochastic field. In the context of the structures, the FRs will be acting as sources. The amount of gain will be proportional to the present amplitude of the FR and to the strength of the gain field. How can we apply potential? There is no way to apply Coulomb's law directly. We don't even have the concept of charge. But we know potential, whatever it is, plays an important role in shaping the structures. The only available parameter in our model is the strength of the gain field. So it must be influenced by the presence of nearby structures in the same way, mathematically speaking, as in normal quantum mechanics. Potential describes a modification of the gain field. As I said, I have discussed these what-ifs fully elsewhere. What you need to know is that these assumptions give rise to solutions which match the Schrodinger results in form and can be made to match them quantitatively. So although this theory has a physical basis, it could easily form the foundation of quantum mechanics. And that would surely help us to understand the Schrodinger equation in the sense I have previously described. Here are some solutions in 2D and 3D for the simple harmonic oscillator potential. I'm going to do something a bit strange. This theory involves orthogonal waves crossing to form rotating FRs, so it is really only applicable in 2D or 3D. But I'm going to look at it in 1D to start with, because this brings out one of the main features which helps to understand the Schrodinger connection. Moving back to 2D or 3D does not change things too much. Look at these 2 figures for a simple harmonic oscillator potential. The one on the left was calculated using standard finite difference methods on the Schrodinger equation. The one on the right is calculated on the basis of the what-ifs just described, with parameters adjusted to give the match. The plots are squared eigenvectors in both cases. You will find me calling these eigenstructures or just structures. In both cases, the psi values are complex numbers and their magnitude has been calculated as psi conjugate times psi. The eigenvalues are shown in this figure. To achieve them requires unphysical values of alpha to be applied. But the 1D simulation is unphysical anyway. We have very few of the FRs interacting, but we are applying the full gain to them. In 2 or 3D, the numbers of interacting FRs is hugely increased, and the value of alpha drops back to something physical, i.e. a lot less than 1. Anyway, I hope that you are convinced that the model is giving results which obey Schrodinger's equation. Now we come to the most important result of all. It is the reason why we get Schrodinger results, but it is so much more. It explains why electrons are fermions, and also why they obey the Pauli exclusion principle. In fact, I have come to believe that it is probably the most important fact in all of physics. See if you agree. Look at this figure. It is a close-up of the central region of the previous figures, but instead of plotting the magnitude, it plots the phase. Recall that the psi values are complex numbers, and that complex numbers live on the complex plane. We can treat their values just as Cartesian coordinates, but their full power emerges when we treat them as defining vectors with a magnitude and an angle. Before, we plotted the magnitude squared. Here, we plot the angle, or phase. The phase calculated by our method alternates by pi radians between each FR. This is not something that was put in any way. The calculation method uses standard matrix eigen software to find these solutions. It took me quite a while to realise the huge significance of this. The first thing to recognise is that there is actually something a bit crazy about the what-ifs. The problem is that the FRs have gains from the background field, but no losses. Finding a stable solution, one which did not vary with time, would seem to be impossible. Electrons would explode as they sucked in more and more energy. There is a more subtle problem as well. If we write the equation for the contributions to one FR from all of the others along the line, and this is why we are looking at 1D by the way, it makes this particularly easy to do, we can see that we get something like this. Ignoring other factors, we see that it contains a harmonic series, 1 plus a half plus a third plus a quarter and so on. But it is well known that this series does not converge. If you keep doing it, you will end up with an infinite answer, unless other factors suppress the problem. But it still feels a bit worrying. Fortunately, the maths inherent in finding the eigenthings has got this all sorted. Because we are adding complex numbers in the complex plane, when the FR phases alternate, their contributions partially cancel each other out. Also, by having phases alternating, we convert what was a harmonic series into an alternating harmonic series, and this does converge. And because the leading contribution term has the opposite sign to the FR in question and dominates the summation, summed contributions are always tending to reduce the amplitude and thus counter the vacuum gains and give balanced solutions. The magnitude of the two FRs adjacent to the one in question is important. They are the dominant terms in the two series. If they are large relative to the target FR, then the contribution is large, while if they are smaller, the contribution is smaller. Let's see how this interacts with the gain field as modified by the local potential. First, think about a long row of FRs, all having the same magnitude and all in the same potential, a flat potential field. In this hypothetical situation, everything is in balance. By the way, I've shown all the FRs as positive for convenience, but they actually have phases alternating. The gains from the local gain field are exactly cancelled out by the negative contributions, so the magnitudes are flat. Now let's consider what would happen if the gain field was lowered below this critical value. Considering the FR at point A, it is not getting enough gain to be in a flat field. It can only be in balance if the amount of negative contributions from other FRs is also decreased. But the two adjacent FRs are representative of the arriving contributions. They are the first and dominating terms in the alternating harmonic series. So the average magnitude of these two FRs must be made lower than the FR at A. This means that the curvature or second derivative must be negative. And this is exactly what we see in the central region of the simple harmonic oscillator well, because it leads to sinusoidal behaviour. Incidentally, you may be curious about what happens when a sinusoidal psi curve crosses the axis, that is, psi becomes negative. What happens is that the phase order flips. So denoting the phase as just plus and minus, you get this sort of picture. You can see this applied in the three-dimensional case here. Phase alternation has been suppressed in this plot, but the phase order switch between the two lobes is denoted by the different colours. Now let's see what would happen if the potential gain was slightly increased above the equilibrium value. Then we require that the two adjacent FRs, which are suppressing the gain, must have larger magnitude to balance things out, and we have induced a positive curvature or second differential. This is what gives rise to the zones of exponential decay on the edges of the simple harmonic oscillator solutions. And this, I would submit, is why there is a second spatial derivative in the Schrodinger equation, and why its value is controlled by the potential gain field. We are using a continuous function psi to represent something physically real, the magnitudes of the discrete FRs. The shape arises from the requirement to balance the positive gains and the negative contributions at each FR. I think that can be understood in the sense of the earlier discussion. This is a lot to take in one video. In the second part, I am going to look at the other main part of the Schrodinger equation, the first time derivative. Please like and subscribe if you want to be alerted when this becomes available. Thank you for watching.